So where were we? So so today I'm going to finish the course today. So I will talk about the exact RG Polchinski's equation, and then I'll talk about the renormalizability of the intuitive idea of why hypothesis is normalized. Do I have to have that?
They are coming, sir.
Oh.
We just get it.
So it will be. So I won't repeat everything I did last time, but I'm just showing you what we did. So we started out, we used a theorem to break up this into a hierarchy. This is the bare action. What we do it in momentum space. This phi is also function B. This is the interacting part, that's the free part. This is the full propagator, which typically can be 1 over t squared. But since your bare theory to begin with has an ultraviolet cutoff, you can put some function here. Instead of cutting off this, you can cut this off with some function which you choose suitably that type, where lambda naught is some UV cutoff which you eventually will take to infinity. So this could be something like that. So it doesn't have to be that. You can have that. But preferably you should use something that's smooth, differentiable and so on. And then we said you can rewrite this as two integrals, d phi L, d phi h, and you can break this up phi L, phi L, phi h, phi h. So I proved this for you that after some overall normalization this is correct. And this delta L and delta H satisfy this. Delta L plus delta H. So where delta L is something similar to this, but with a lower cutoff. So this is of the form, let's say, k of p squared by lambda squared, and then this is just the difference of the two. Okay, so delta H is this delta minus lambda. So what we're doing is we have 0 to lambda naught, then we have a lambda which is a moving scale, and you're integrating out these guys. This is basically your phi. But remember that it's not a sharp cutoff. The other point you should remember is that this phi h is, delta h is the form k p squared by lambda naught squared minus k p squared lambda squared by squared. Yeah. Thanks. So clearly, in the limit lambda naught goes to infinity, both these arguments become the same. Sorry, in the limit that t becomes very small compared to lambda naught, both arguments go to 0. So there will be a cancellation. You can put that explicitly. So you see something like for small lambda naught squared, which is 1 minus. So the 1 cancels, and then you get a term proportional to p squared. So there's p squared in the numerator, p squared in the denominator cancels. So the whole at p squared equals 0 disappears. So this has not singular at squared equals 0. So that's something you should keep in mind. And then what we did was to perform this integral and write this as plus this is all inside Si lambda. This is the definition. This is defining that. So that defines. So this equation defines this. So whatever you get after doing that integral, which is going to be a function of only phi L, whatever you get is that. This is called the interacting part of the Wilson action, and this whole thing is called the Wilson action. And as I said, because we've integrated over only high energy modes, there is never any propagator which is singular at p equals 0. So this object is completely finite. Yeah.
So we wrote the whole range in low and high energy. Now, when you're saying that delta H is not singular and p square is equal to 0,
Yeah.
does it change? I mean, p square is the delta H is valid in the high energy.
No, I have given you an explicit form. Valid is a loose word. This is an explicit form for delta H. I've given you an explicit form for delta H, right? It's not that it's valid. This is the form for delta H. So what is the, okay, so maybe I should explain that. What is the property of this function? So let's plot this function. So this function for p squared equals 0 is 1. For p squared much larger than lambda naught squared it's 0. So it goes to 0 here. And basically around lambda naught it starts to fall off. Right? That's the form of the function. So what does that mean? That means that for values of p much larger than lambda naught, this function goes to 0, so it's not propagated. Similarly, this is lambda naught. Similarly, k p squared by lambda squared is the same function, except it falls off like this. Okay. So when you take the difference between this and this, basically this part cancels out, where it's 1, that cancels out, and this part is anyway 0, so it propagates mainly non-zero in this region. So this function delta H is non-zero in this region, it's 0 in this region because it's subtracted out, and 0 in this region. So you get a function that looks like this. So that's the form of delta H. Okay. So it only propagates modes in this region. Certainly for p squared equals 0, it's exactly 0. So it does not propagate the p equals 0. So the p equals 0 mode is not integrated out at all. And of course, these modes anyway don't propagate. So the word is not that it's valid, this is the form of the function, form of the propagator. So clearly p squared equals 0 is not propagating, so that's why there are no singularities. So there are no infrared divergences. And anyway there are no ultraviolet divergences because you will eventually get infrared divergences as you move lambda all the way to 0. For arbitrarily small lambda there won't be any infrared, but if you make it exactly equal to the limit, you will recover all your infrared divergences if it's there. Okay? But ideally what you do is you solve your differential equation, you get a solution that has no infrared divergences, and you can make it valid for arbitrarily small lambda. Then unless there is some problem or vacuum instability or something, there won't be any artifacts, which often happens in perturbation theory. So maybe I should make a point here. See what happens in perturbation theory, that even if your theory is actually infrared finite, you will see divergences order by order. Why? Because in perturbation theory what you do is, you have a state, what you're actually doing is, you integrate out everything from here to here, then you integrate out everything from here to here and subtract. So you take your integrals involve a full 0 to lambda and then varying that cutoff. So you get two infrared divergent things in which the infrared divergences cancel. But if you do it this way, it's manifestly finite. Okay, so your solutions of the RG don't involve subtracting out this region. You're not doing that integral at all. In ordinary perturbation theory, you do from 0 to infinity, and then from here to there. So then from here to there, and then you subtract. Right? So at every stage it's infrared finite. Whereas if you do ordinary perturbation theory, only the final solution is infrared finite. The order by order is not finite. Okay, so this is Wilson action, this whole thing. This is the interacting part. So now I'm going to derive differential equation for this. And that's the Polchinski equation. So now, so let's start with the definition. So what I'm going to do is I'm going to take this is the definition. So this is my z. So let's see. So what is this? So d phi h e to the power minus half phi h 1 over delta h phi h minus si d phi l plus phi h. This is e to the power minus si lambda phi. Right, that's the definition. So now what I'm going to do is to differentiate this. So we'll define lambda as lambda naught e to the power minus t, so that lambda dB lambda which is minus dBt. So t is in the direction of decreasing lambda. So we just differentiate this with respect to t. Okay. Or you can do lambda dB lambda. So you get minus. So I'm going to act with this one, and I'll get this. This is my left hand side. Times, of course, this function. So I'll put that. What is the right hand side? So the where is the lambda dependence in this? This is phi h. This lambda dependence, where is that in this action? It only comes in through here. Right? This is a bare action. This doesn't know about any small lambda. I mean, capital lambda. It's just an action. At best, it can have lambda naught. It doesn't have capital lambda. So when I differentiate, I just have to differentiate this. So I get. So I just write it this way: minus half phi h lambda dB lambda of 1 over delta h times phi h. So remember, this is all p and minus p. This is true. Times the same thing. So that's the left hand side. So this you can simplify and write this as minus del h dot by square. So that's the limit. Okay. And since it's just a function of p, it's all multiplicative. So this is so I get plus half delta h dot. So like phi h delta h dot by delta h squared phi h times all that. So I'll just write this as e to the power minus s lambda. Oh, maybe I should call this sb. Yeah, sb. I have an integral here, right? So phi h. So the whole thing is inside the integral.
The interaction part you are leaving out, there are couplings, right?
Yeah, but this is a bare action. It doesn't have lambda. Bare action has no knowledge about lambda. Just your initial value.
Lambda 0.
Yeah.
This quadratic coupling.
Yes. It has lambda 0, but it doesn't have any lambda. So we are keeping that fixed. We are just varying this. So that information is entirely in this delta h. Through this, where delta h is this. This. So this has a lambda.
So that bare coupling running with that lambda 0 has no effect on this.
No, at this point the bare coupling is not running. You have some initial condition. At lambda 0 you have some action. You don't touch that. That's untouched. Then you're just integrating all these modes up to lambda. Then you see what happens when you change this lambda. This is held fixed. Okay, so that's a good question. So SB is held fixed. So this is held fixed. Has no knowledge of lambda naught. Oh, sorry. It's just held fixed. So that's the derivative. Now I'm going to compare this expression with another expression and you see that they're the same up to some factor. So I'll do another operation, which is, let's differentiate both sides, act on LHS and RHS with d squared by d phi p. Okay. And so when I act with d by d phi p, what do I get? You get something from here. Wait. Sorry, I missed one step. I should have done that. Okay, back up. I wrote this in another form, which I will do that now. So before I do that, let me rewrite this in another form. So I'm going to call this whole thing phi double prime, and this phi h will be called phi double prime minus phi l. Okay. Change the variables. And this d phi h I will write as d phi double prime. So change variables. To phi double prime and phi l. So what does this become? So this becomes d phi double prime e to the power of minus half phi minus phi double prime 1 over delta h phi minus phi double prime, and this has a p and a minus p. Then there's a minus SIB phi. Okay. Sorry, missed that. Sorry, SIB phi double prime. Wait. Phi double prime. No, I think I did something. Oh, sorry. Made a mistake. Wrong. Where is this? So this is. This is correct. Yes, this is correct. This is correct. Yeah, this is fine. So now, so this is correct. So act with. So I haven't done anything, just a rewriting of variables. Act with d squared by d phi p. Okay, so this step was crucial because this phi now doesn't act on this. This is phi double prime. It acts only on this. Okay, so that's why I had to do this change of variables. So let's act with this. It differentiates that. So there will be two terms. So if you do one, let's do it one by one. So if you differentiate this, you will get d by d phi. The half goes away, and you get 1 over delta h phi minus phi. So when I do those differentials, I get d by d phi minus p of this p times e to the power of minus the whole thing. Where this whole thing is again phi minus phi double prime. 1 over delta h phi minus phi double prime.
Your phi is phi l, right?
Yeah, phi is phi l. Because the final result is going to depend on phi l. Yes, I should have said that. So phi l. Of course, at this level it's just a variable, so it doesn't really matter. Now,
this is the relevant field at lambda, right?
Huh?
This is the phi is the relevant field at lambda.
Yeah.
Until we are integrating.
Yeah. So now you get two terms. One term acts on this, and one term acts on this. When you act on this, you just get this piece. This is just a function of p. There's no field in it. So it's a field independent object. So when you integrate, you just get a number. That's a proportion to the partition function. So we don't worry about acting on this. Okay? So we'll act on this second time. So when you act on that second time, you get again another same factor with a half gone and the same thing. So what you will get is two factors of this. So you get phi L minus phi double prime p, phi L minus phi double prime minus p, and then two factors of this times all this. And this is all inside the integral sign. Okay. Is this clear? So the crucial point is that after the change of variables, this is untouched. Acts entirely on this. So now you look at this structure and you look at this structure. So if you want to call this phi h, you can call it phi minus phi L. Okay? So it's the same thing. So you can make the same change of variables and write this as phi minus phi L. Oh, so let me make this. Sorry, this is. I should have done the same thing here first. So let me write this as the same thing. So I write it in the same way, and then this will become phi double prime minus phi L, and this is E phi double prime. Same change of variables that I do here. This has a delta h dot. This has a delta h dot by delta h squared times so I'm using the same notation now and writing it here. I didn't do that previously, but this is the same change of variables. But now you compare this with that. They're almost the same. Only difference is there's an extra factor of this delta h dot. Otherwise, it's the same thing. Okay. So the conclusion is that this operation is the same as this operation up to this factor of delta h dot. So you get an equation. The delta equation here. So you get an equation says, so I call this one, this I call 1, and this one I call 2, and the relation is that 1 is basically half lambda d delta h d lambda times 2. This is what we call it minus delta h dot. So if you write this out now. So what we did is to compare the right hand sides. So write here for delta. So what do you get? So you get minus lambda dd lambda of si lambda phi. So now final variable you can call it phi L or you can call it phi, doesn't matter. So this is what this gave. This must be half lambda d delta h by d lambda times that object, which is this thing, which is so at d squared by d phi squared on so So what is this acting on? This is acting on this whole thing. So this is equal to b squared by d phi l e d phi l minus b. What this whole thing is nothing but e to the power of minus half e to the power of si lambda phi l. Remember, this object was defined to be, that's the definition of si lambda. So this whole thing, after doing the integral, is just e to the power of minus si lambda. That is the definition. Okay. Fine. So you're actually operating on that. Okay. So let's operate on this twice.
Should there be a second piece when delta phi acts on the argument of the exponential?
This is that piece. See, this, when it acts once, it gave this. When it acts twice, the second time it's acting on that. When it acts on this, it doesn't give anything. It just gives 1 by delta x, which is field independent. So we neglect that. So it acts once on that and it once on that. Okay. So what we have to do is to act on this. Instead of writing it in this form, we write it in that form and just act on that.
Some kind of exact propagator, is it?
Sorry?
Some kind of a propagator.
This one.
No, after different, yeah.
Yeah, so what you get, so if you act twice, you will get this equation, delta Si lambda by del phi p. So I've called phi L if you want. Minus so when you act twice, this is what you get, and times the whole thing. So there's an overall factor of e to the power minus si anyway, both sides, which you can cancel. So this is acting on the exponent. So this factor comes down, this comes down, and then you can drop this and drop that. Okay. So you get an equation like this.
Non-linear.
Okay. So that's the equation for this is what is called the exact RG. You know, this form, although this form was first written down by Polchinski, it's basically a variant of the Wilson had in his original paper exact RG, and Polchinski used the same thing and he varied a little bit, and he got this equation in a continuum form. So this is called Polchinski's equation, often in the literature. So it's an exact RG. You can see this is your interaction. So what you have to do is the differential equation you have to solve. You start with some action at lambda equals lambda naught. When lambda equals lambda naught, this is your bare action. You solve the differential equation and evolve in lambda, and you see how this changes. So you have an initial condition and an evolution equation, and you solve it. Diagrammatic. So I'll do one more thing, and then we'll. So this is the equation for. So let's write. So e to the power of minus half phi L 1 over delta L phi L minus Si lambda times phi L. This is our Wilson action. So we can call the e to the power of S lambda phi L. What we have is an equation for this. This has a simple lambda dependence. You know explicitly what it is. So we're getting an equation for this. But if you want, you can write this equation in terms of an equation for S.
I couldn't follow up with that. How did you got this equation?
This one. So what I showed was that you start from the definition of this integral. I showed that acting with this on the right hand side gives you the same thing as acting with this on the right hand side up to that factor of delta h dot. Okay? But the right hand side, this whole thing is actually just that. So it becomes an identity for this object, or then equation for. So this is a equation. So let me do. So I was going to say that I'm going to now let's do the following way. Let's write Si lambda is S lambda minus this part. So everything is fine. I can drop the subscript L if you want, but you know the subscript L, it's not a property of the field, it's a property of the propagator. Field is just a variable of integration. So, but for conceptual reasons, we put this L to show that it's a low energy thing. So it's all the information that is low energy is in the propagator. So you can now plug this into that. Okay, so the left hand side, dsi lambda by dt is ds lambda by dt minus the derivative of this, which is half phi L delta L. So d by dt is now minus lambda dd lambda. Half phi L delta L by squared phi L. And delta S, so this goes to the left hand side by delta phi p is delta S lambda by delta phi p minus 1 over delta L phi minus 1. Just acting on that. And this will come twice, and then the second derivative acting on this twice will give me a field independent part, which is not interesting, and second derivative of this. So you can substitute this and that into that equation for the right hand side, and for the left hand side you substitute this, and you get an equation for the whole action. So I'll just write down that equation.
Sorry, it reminds me of some WKB wave function equation.
WKB.
Yeah, WKB wave function equation satisfies some similar equation, right? Because
Yeah, it's a very generic form of the equation. So if you look at Wilson's original derivation, it is motivation, something like that. But it's exact, because it's all being done in terms of function.
yeah, I guess Schrodinger equation, if you wrote the wave function as e to the
Yeah.
s, is, then you will get this structure.
Yes, yeah. So it's a very generic structure. So what you get? So if you so left hand side you get
Get the equation.
ds lambda by dt plus half phi. Now. Yeah. Okay. So I dropped that L. So this is minus half delta h dot. So I collect the terms involving this first. And then there's a cross term. When you square that first derivative, you get a cross term like this, and a term of the form phi p, phi minus p by delta h squared. That's just squaring this. Just squaring that. Now you notice that delta h plus delta L is delta. This has no lambda dependence. So delta h dot plus delta L dot is 0. So this delta H dot is actually minus delta L dot. Okay? So this you can write as plus half delta L dot. So in terms of the origin. And then you see that this cancels. These two terms cancel. So this cancels with that. And you get an equation for S. So find the equation for S. So let me just write it for completeness. So this is Wilson's equation, or Wilson's equation as written by Polchinski, which is usually called the Polchinski equation for the full Wilson action. It's equivalent to that equation. This is equivalent to this, same thing. And of course, it follows trivially that pure Gaussian action is a solution of this, because that's just saying that S is 0. So if you start with a pure Gaussian action, Si is 0, so it trivially satisfies this equation, 0. So obviously it satisfies this also. Is clear? Putting Si to 0 is the original Gaussian action. Yes. So if you put S equal to 0, that equation is trivially satisfied. So that means this equation, this term has to satisfy the Wilson equation. So this solves Wilson equation. Is this clear? So that completes the derivation of the exact RG. There are various versions of this, as I told you. Wilson's original form was almost this, except this part was the same. Here he had some other function. His derivation was slightly different. This function was slightly different. So, but this is actually a very convenient form. It's convenient because you get a nice equation in terms of S interaction like this. What is the interpretation of this, either of this or of that? Diagrammatically, what does this do, these terms? So if you think in terms of vertices, in terms of the action, Si has vertices, so you have some vertex. So let's say these are your vertices with arbitrary numbers of 5. Okay? What does this thing do? It combines two of these with arbitrary numbers of 5, contracts one leg with this propagator, delta. So as I said, this can be replaced by, this is delta H with the propagator, and then differentiates that. Okay? So what you're saying is, you connect this thing, what is the effect of doing this Feynman diagram? How does it change your action when you differentiate that? So it generates a new vertex which involves a higher point function. So this was a n point function, so this has n minus 1 free legs, and this is some m minus 1 free legs. You will get an n plus m minus 2 point function after doing this. So for instance, if you start with a quartic, this will be a cubic, this will be a cubic. So you get a 5-6 vertex connected by a high energy propagator, which at low energies is just a number. So this has no pole at p squared equals 0. So low energies is just a number. So you get a effective 5-6 vertex from this. What does this do? This just does something like this. So if you have a vertex like that, it removes 2 legs. So we start with a quartic piece, this will make it a quadratic piece. If you start with a quadratic piece, this will become a constant. So it just closes one loop, but integrates out only the high energy part of that. So you get a lower energy vertex with 2 fewer legs. So this tells you how diagrammatically how the action evolves. So what else did I have to say about this? Okay. So as I said, there are other versions of various exact RGs you can write down. People call them, just to complete the story. This is not working. So let's see.
Well, 13.
Okay. So I want to talk about the renormalizability of hyperbola. So as I said, there are other versions where you do variants of this. So this is your lambda naught, this is your lambda, this is 0. So you integrate out this with a source. Okay, so you get a generating functional which has information about things that you integrated out. Here, the information about the things that you integrated out is contained in this field, this action. You can do other things. You can put the j and keep information about that. So this will be a generating function in the usual sense, except since you've only done up to here, you have a IR cutoff. And then you can take that generating function and do a Legendre transformation and get a effective action, the one particle irreducible action, and get an analogous equation for that. That's often called the functional RG, which is developed later on by some others. People that equation has some simple form, and a lot of work on RG uses this form rather than this. Okay, so that's just some general information. So there are no questions about this. So you've got the exact RG. You can go and read up Wilson's original derivation, which is quite different. I want to talk about the argument for renormalizability of the 5-4 theory as given by Hodzinski. So,
Sorry, can I just ask?
yeah,
So you said the free theory or Gaussian model is a solution.
yes.
Any other exactly known solutions?
The Wilson-Fisher fixed point. Oh, by the way, yeah, I should make one point. There are two things here. One is the solution of this equation. Any action you write down has to solve this equation. Because that's the definition of the action. Right? The other thing is the fixed point of this equation. So the fixed point of the equation is basically saying that the couplings don't change. You have not only have a solution of this action, it's a solution that doesn't change. Okay? And I don't have time to talk about that, but it's fairly easy to see that Gaussian theory is not only a solution of this, it's also a fixed point. Because it's extremely doesn't have any parameters in it.
Sorry, I thought any action source. I thought if you start with a renormalizable theory and integrate it out till lambda, whatever the effective action you get solves this. Not every action.
No. Okay, what I mean is any Wilson action that you get by integrating out is a solution of this. Conversely, you solve this differential equation to get a Wilson action. So by definition, a Wilson action is something that solves this equation. Okay? So in that sense,
So the Wilson
the
action
Gaussian.
is you start with an renormalizable action and integrate till the.
Well, at this point, there's no statement about any renormalizability because in principle you have a cutoff lambda naught. I'm not talking about taking lambda naught to infinity. Lambda naught is not being touched. So you just start with some bare action at lambda naught. You integrate out. Whatever you get is the Wilson action, and that Wilson action, half fourth theory satisfies this equation. So instead of doing that integral, you could just solve this differential equation with that initial condition. Okay. So it is true that this in particular will solve this equation because it doesn't do anything, it's there. But the non-trivial thing now is to ask what are the fixed point solutions of this. So this is one fixed point solution of this. Another fixed point solution is the Wilson-Fisher, so on. So that's the next order question.
Fixed point meaning the right hand side itself is 0.
Well, okay, you have to when we did the fixed point in the original thing, remember we did some rescalings to keep the cutoff at 1. So after you do that rescaling, it should satisfy the fixed point. So modulo rescalings basically that's it. But that rescaling will introduce some extra terms. So you can see that the Gaussian theory, if you don't rescale, it has an explicit lambda dependence, it's not a fixed point. So you have to rescale your P and lambda, so there's no lambda. Okay, so let me talk a little bit about renormalizability. Okay. So we talked about renormalizability of the marginal coupling in the sense of we had these log divergences and we said the structure of the equation, the evolution was such that it was perfectly clear that here it could be renormalized. You can make it finite because it's just a translation in variance. You can calculate beta functions and so on. So analogously, we have to ask the questions for the more general action. So you have some action in the form of du phi plus lambda. This is your usual thing. So let me call it G first. So it's G4. When I add, to begin with, let's talk about this G6 phi 6. Okay. Before I talk about that, if you remember when we talked about the epsilon expansion, we talked about the effect of the adding the irrelevant variables on the fixed point. And we said that there's a consistent way in which this is higher order in epsilon. Not only it's higher order in epsilon, because of the damping, you can do the sum is convergent, so it doesn't destroy your fixed point. We analyze the Wilson in the Wilson recursion relation, the effect of the W term. Analogously, we have to do that here. What is the effect of the irrelevant operators? Okay. Now I'm going to say this once now and once later, but this operator can be called irrelevant or non-renormalizable, and they mean slightly different things. Typically, if you call it irrelevant, you would write it in this way. So this theory is a bare theory with some cutoff lambda naught. On dimensional grounds, this has dimensions of 1 over mass squared, right? Because this is dimension 6. So we're in 4 dimensions, let's say, d4x. So this is dimensionless, this is dimensionless, this is dimension 1 over mass squared, which I'm writing as a dimensionless coupling by lambda naught squared, cutoff scale. Okay? And this is just lambda 4. So lambda 4 and lambda 6 are dimensionless. And G4 and G6 have dimension. So this has dimension 0 and this has dimension 2 or 1 over minus 2. It's 1 over mass squared. So it's a squared. This is what we usually call an irrelevant operator. And why do you call it irrelevant? Because it is generated in this operation. So if you start with a phi 4 theory, this will give you a phi cube, and you get a phi 6 term. It's generated. Okay. On the other hand, if you put it in the bare action, not with the lambda naught squared, but with a term of the form lambda 6 by n squared, where n is some parameter in your theory, nothing to do with the cutoff. This is non-renormalizable. It's the same operator. The issue of whether it's renormalizable or not has to do with this coefficient. If it's in the form 1 over lambda naught squared, it's irrelevant. So what I want to do is to write down the beta function equations. So we're talking about this kind of term, not that. Okay? And I'll come back to that in a minute. And I want to show what is the effect of terms like this which are generated. So terms like this are generated in this operation, and when you prove, so what is renormalizability in the context of phi 4 mean? It means that when you calculate Feynman diagrams for scattering process, you do not generate divergent terms as coefficient of phi 6. Divergent meaning as lambda naught goes to infinity, those terms should not go to infinity. Because if you generate divergent terms of this type, then you will have to put that into your bare action as a counter term, and then you introduce one more new parameter. So in this context, renormalizability simply means you do not generate divergent corrections to this. Okay? So the simplest way to intuitively understand that is to try the toy models and see the flow, and you'll see what is the property that makes that happen. So so let's write down the beta function equations first. dg4 by d lambda. So remember, the strategy for proving renormalizability is not to do Feynman integrals diagrammatically, but to study the flow of couplings as you go along the RG. And you want to show that nothing bad happens to these couplings. Of course, this order by order may have log divergences, which you know how to sum that using the beta function. The question is what happens to this guy. This is the irrelevant. Does it go to a nice limit or does it go up? So let's write down the differential equation. And this is dimensionless. So you're going to get terms, dimensionless terms. So you can write it like this. Make everything dimensionless. G6 has dimensions of 1 over n squared. So this makes it dimensionless.
So so this lambda, how do you try to do this lambda? How this lambda system linked to the non-linear?
No, I want to show. Well, what do I want to show? That in general, this Wilson action has all kinds of terms. Right? When you do the RG, you will, even if you don't have this to begin with, you will generate it. The question is, does lambda 6 go to some 0 or finite value, or is it going to blow up? Because if it's going to blow up, that means you have to add counter terms and change your Baire theory. So what we're going to argue is that nothing bad happens to this coupling constant. It goes to some nice finite value. It's not that it has no effect, but its effect is very small. So let me just write down the differential equations. What I'll do is I'll just take some simple toy equations. So on dimensional grounds, this has dimensions of mass squared, so this has to be of the form, 1 over mass squared, so this has to be the form times the dimensionless guy. Because there's no other scale in the problem, when lambda it has to come out like this. So now let's write this in terms of, so we'll define lambda 4, which is G4, and lambda 6 by lambda squared is G6. So this is basically lambda 6. So if you write the same equation for this, you'll see the following: lambda E lambda 4 by E lambda equals beta 4 6, and lambda D lambda 6 by D lambda minus 2 lambda 6 is beta 6. So this is the structure. This is the all-important term. This is the analog of the fact that when you did the recursion relation for W, it was W prime is 1 by 4 times W. WL plus 1 is 1 by 4 WL. It damps it in each iteration. So this is what that is doing here. And as again, it's for purely dimensional reasons. So what I want to do, so the philosophy of this argument is to, instead of doing perturbation theory and diagrammatics, study these equations. That's philosophy. Study the equations and show that they have well-defined behavior. And instead of studying it abstractly, I'm going to just, you get a feel by taking some concrete models like we did, where you can study the time evolution or lambda evolution of an equation, and because you have tools like Mathematica, you can just play around and build up your intuition. So here's a simple equation. So let's start with the simplest equation where there's no coupling. So this equation, which doesn't have this nonlinear piece, has a simple solution. So this tells me that lambda 6 is some constant times e to the power of minus 2t. So remember the t as before is lambda naught e to the power of minus t is lambda. So evolution in t is going to the infrared. So this is the statement that, so at t equals 0, if you start with some value, it just gets damped. Okay? So lambda 6 just damps to 0, which is what we saw in the recursion also. And then if you modify this equation, so what is the typical equation for lambda 4? Something like this, some sign here. Okay? So this will give you an equation that solves it. So you get something. So solution. We know the solution of this. It's lambda 4t. Some minus is 1 by minus t plus 1 by. And this you can call as lambda 6 0. So this is the typical solution of these equations when there is no coupling between them. Okay. This equation is solved. This is the usual beta function for marginal coupling, and this is the scale. This is the log lambda running and so on. So here lambda 4 for large t goes to some value, finite value, starting with some finite value, and this one just goes to 0. Simplest behavior. So what happens if you now couple them? Let's do the simplest coupling. We just add a term here. So what's going to happen is this guy is going to feed into that, and that guy is going to feed into this. So to study the effect of that, you can just put in a time-dependent piece there and a time-dependent piece here, and see what the solutions look like. So you can try something like this. d lambda 6 by dt is this plus some function of this type. Just try that. This is a typical functional form for g. Okay? So here you're going to get some power of g here. And you can write down, you can solve this pretty much exactly. You get lambda 6 is some constant which depends on the boundary condition plus some well-defined term, I'm just writing it down, times the exponential integral of 1 to c. So this is a particular solution. This is the thing that depends on the boundary conditions, and you can this thing goes as basically as 1 over t, and I wrote it. So what is your conclusion? Your lambda 6 gets contributions due to feeding in from the g, which is of this type, and a damped contribution like this. Okay? So if you plot, and now you can also put this solution for lambda 6 into that equation, see what you get for lambda 4. For instance, you can write down d lambda 4 by dt equals lambda 4 squared. Suppose your nonlinear term is something like this. So to lowest order, I put in this solution for that. See what you get. You get a solution for lambda 4 that looks like this. You get some constant plus t times e to the power minus, this coefficient is, let's call it W naught. So I'm putting in this solution. T times W naught e to the power minus 14 plus, with some numbers are not important, and the denominator is also something like this. You get some linear term in t, which is like that, plus some W naught e to the power minus 4t, etc. This is the form of the solution. Okay. So what is happening to your lambda 4? It's your original solution, which had that form, is getting modified by this piece. But you see, the effect of these pieces are all damped in time. They're all of the form e to the power minus 4t, which is your original damping. So the conclusion of this is very simple. Both lambda 4 and lambda 6 go to well-defined limits. Lambda 4, the original well-defined limit in the absence of lambda 6, is modified slightly by the addition of these terms. Lambda 6, lambda 6 is interesting. Even if you started out without any lambda 6, it gets generated by the lambda 4 terms. So that's we saw that even if your 5-6 interaction is 0, you're going to generate it when you do the corrections. So this is that generated piece, which is some fixed thing, but it's finite because it doesn't go up. And the influence of your initial lambda 6 is damped. Okay, so now you can, based on this intuition, you can plot curves, and then you can talk about the continuum limit. So you get curves in the lambda 4. So this is, let's say, lambda 4. This is Yeah, this is lambda 4 and this is lambda 6. Or you can plot it against, well, let's plot it. So you get, so your typical the curves look like this. Or I can plot it against t, let's say, lambda. So you can see what's happening here. The lambda 6 goes, so let's say at this scale, this is your bare thing. Let's say lambda naught is over here, and you choose your lambda 6 to be 0. Okay? And then you evolve it to the infrared. Even if it's 0 to begin with, you will generate it because you added this piece. This is the contribution of the lambda 4. So your lambda 4 couplings will generate lambda 6 couplings even if they're 0 to begin with. So that's the generation. And if you start with a different point, say here, it will follow a trajectory like that. But the effect of the initial condition, so let's say here it's 0 and here it's some other value, this difference is getting damped. The damping is this factor. Okay. So the bottom line, what is the bottom line? You start with different initial values of lambda 6. They all go towards same value. The dependence on the initial condition gets damped by this factor of e to the power of minus 14. So that e to the minus 14 came about by dimensional reasons. It's from here. That's this minus 2 there. Okay. So whatever your initial condition, even if it's 0 you get generated, but they all go. So by the time you go to low energies here, your lambda 6 is determined to within some region of order e to the power of minus 14. So they all converge. Okay. So they have well-defined finite limits. That follows from an elementary RG flow analysis. You just look at the way the equations flow. So continuum, what does a continuum limit mean? Continuum limit means you want to take this initial point far away and let it evolve. So even if your lambda, and you don't have to start with lambda 6 exactly 0, you can start with some small lambda 6 here. You could have, so as I said, you could start with this. So at lambda naught, you can put a small lambda 6 here and let it evolve. It doesn't matter. All that will happen is your final value of lambda 6, it's not going to be 0, it's going to be some finite value, but the value doesn't depend on your initial condition. It gets damped as e to the power minus t. So there's a well-defined limit. So the irrelevant operators of the theory don't affect the beta function flow equations. And I mean, in terms of the final value of lambda 4 and lambda 6 continue to be well behaved, independent of your initial value matrices. So the statement about renormalizability of phi 4 is just this, okay? That even if you include the effects of the irrelevant operators, they don't affect your final value of those terms are finite. If lambda 6 were to diverge, then you would be in trouble. Then you would say the theory is not renormalizable. So, let me just.
Lambda 4 could also be diamond, right?
Yeah, lambda 4 has an usual. If you expand this in perturbation theory, you saw that it goes as log lambda, but then that you can renormalize. So the renormalization of lambda 4 has to be done. The question is, what is the effect of lambda 6 on it? And the statement is, its effect, it renormalizes lambda 4, so the precise value of lambda 4 is going to change. But the value of lambda 6, there is no huge lambda 6 generated. Lambda 4 anyway is going to diverge in perturbation theory and you have to renormalize. But if you follow the beta function, you don't put some finite value. But the crucial point is lambda 6 also doesn't do anything funny. And that's entirely because of this factor of minus 2. And where did that come from? That came from the fact, the dimensional analysis. So this is the 1/4 in your regression relation. How can this be spoiled, this whole argument, if this minus 2 is modified to something positive? So if your corrections, whatever you put here, change this coefficient, so by renormalization, the dimension of your operator can change. Dimension, it doesn't always go with, you cannot get dimension minus 2. So typically there will be some dimension here which will change. And if that dimension changes and makes it positive, then this argument breaks down. So the statement of perturbative renormalizability is simply the statement that the naive dimensional analysis which says that these couplings are damped, and this continues to hold in perturbation theory. So if you accept that couplings is small, renormalizability follows.
Lambda is equal to 0. It's never comes up.
Lambda 6.
It's irrelevant, right? So, if
No, but that's the whole point. It doesn't go to 0. It will go to some finite value. Because it's generated by the lambda 4. Even if you set it to 0, it gets generated. But I told you there's this, this diagram. So if you have a lambda 4 non-zero, you will generate lambda 6.
but in IR, it shouldn't matter.
No, this should be there. So you can see that the solutions, have that property. Sorry, lambda 6. There is a constant piece. This is the effect of the at any t. This is literally take t equals infinity, but for any small t, it's a power, it's a log. So this is going to be non-zero. So this is generating lambda 6, even if you set that to 0. So that's why the solution always has some piece.
What is the form of this EI?
This is an exponential integral. This is going to form e to the power of plus 2t divided by powers of t. So this minus 2t cancels the plus 2t and 2t. So the crucial point is not that lambda 6 goes to 0. It doesn't go to 0. It's finite. But it has no sense. It has no the dependence on its initial value is damped out. So you don't care what you started with. It's always going to end in some range over here. So that in that sense it's irrelevant. You don't care about its value in your bare Hamiltonian.
So, are we connected to the that were non-renormalizable?
It's a non-renormalizable thing. If you work this backwards, it goes to plus infinity. Okay? So it's my photo. So so this, what does this damping mean actually? Damping means that your correction terms of the form lambda squared by lambda naught squared. This is the factor of e to the power minus 2t. Okay? But suppose your initial term was not lambda naught squared but an m squared. Now there is no damping. Because for instance, if you work backwards, lambda goes to infinity. As lambda goes to lambda naught, this is going to become arbitrarily large. So suppose this is a mass of 1 GeV, and you take your lambda to m Planck, this is going to be a huge number. Okay? So your bare theory will have an infinite value of phi 6, which means you have to have a counter term for that. It's not defined. So the crucial point is this kind of thing is what traditionally is called non-renormalizable. This makes theory non-renormalizable because in your bare theory it becomes infinite. So at finite values or at very low energies, whereas this thing is damped with e to the power minus 4t, if you multiply, see instead of starting with this, if you start with this, then effectively it's like starting with the other thing but a factor of. So this is a huge dimensionless number that's multiplying lambda 6 which diverges. So it's like saying your theory in the same variables had an infinite value of lambda 6. As lambda naught goes to infinity, it has an infinite value of lambda 6, and then it's divided by lambda naught squared. So the bare theory has the dimensionless coupling in your bare theory has to be infinite. So that makes it non-renormalizable. But for any finite value you start with, lambda 6, it's going to be a term of that type and its effect is damped. So the word irrelevant and non-renormalizable has a different connotation, it refers to the same operator. So you cannot add a term like this. You cannot add a term like this to your rectangle. That will screw up, bare theory will diverge. But you can add terms of this type and they're anyway generated. So this argument doesn't depend on arguments about adding counter terms and so on. So I just mentioned that diagrammatic point. I just wanted to mention that and stop. So in terms of diagrams, let's look at these diagrams. So this is of the form log lambda naught by lambda. This is lambda 4 squared. Good. And as I said, you can see this diagram has 3 propagators, so it's d4p, what about p6? It's of that type. Okay. So this is going to be of the form, when you integrate it, it's going to be from 1 by lambda naught squared, just on dimensional terms. So this is the small lambda naught that you get, small lambda 6 term that you generate. So this is effectively a lambda 6 of order 1 divided by lambda naught squared. So this is allowed. And terms like this, so if you had a lambda 6 interaction, okay, so this is a lambda 6 interaction and a lambda 4 interaction. This integral will be something like lambda naught squared by lambda naught squared. So this will give you a piece of the form lambda naught. So this is a quadratically divergent piece of order lambda naught squared. This will have a lambda naught squared in the denominator for dimensional reasons. This integral will give you a log divergence. Okay. So what's the conclusion? Even when you add a lambda 6 vertex, you generate the same log divergence that you had without lambda 6. No further, it doesn't get any worse because this cancels this. So it's crucial that you start with a 1 by lambda naught squared. So it kills this lambda naught squared. And you get a log divergence. So this will modify the theory with only lambda 4, but it's the same type of term. So it's a finite modification. Whereas if you had a 1 over m squared, then this would be an infinite modification. So this is the Feynman diagram way of saying this fact, but this is not a good way of saying it because you have to do it to all orders and very complicated rules. But in terms of beta functions, flows, it's very clear what's happening. All you want is that the anomalous dimensions do not overwhelm the canonical dimension. Okay, so I think I'll stop. I will urge you all to go and read the original papers by Wilson.
Last class.